investigate some of the techniques and other things that we've developed over time to handle architecture and design agilely. But I'm going to start with the poetry of Donald Rumsfeld, who very famously at one point said, there are known unknowns. That is to say, there are things we now know we don't know. But there are also unknown unknowns. There are things that we do not know that we don't know. It turns out this is the really hard part about software, are the unknown unknowns. The known unknowns are okay, because when you start a project, you kind of know there's some things that are lurking. It's like, oh, I don't really know the full details of that, but I can reserve some time for that in the project, and we can handle that. Those are the known unknowns, but the unknown unknowns are the ones that always nail you, because you don't even know that you're supposed to be looking for these, and then all of a sudden they pop up, and you haven't had any planning whatsoever for them. Big upfront architecture and design fail because of unknown unknowns. There's just no way to resolve those things, because, as it turns out, the future is really hard to predict. And that's what you're trying to do if you do a whole lot of elaborate architecture and design work up front. You're trying to predict the future by saying, here are the constraints that we know are going to happen in the future, but you're always wrong about that. And so in the Agile world, we said, instead of trying to make our predictability better, because predicting the future is just flat out hard, my mother-in-law at one point just turned to me with disgust and said, those lottery numbers, I just can't figure out what that order is on any given day. It's a really hard problem. Predicting the future is really tough. And so what we've done in the Agile world is say, well, can we design some techniques that allow us not to have to do all this work up front, but instead add flexibility into our architecture and our design. And so let's talk about that for just a second, this distinction between architecture and design. Martin Fowler, I think, did a really good job of defining this distinction in a white paper that he released probably more than a decade ago now, but it's still available on his website, called Who Needs an Architect?, which is about the role of the architect in Agile projects. And in that white paper, he identified or gave my favorite definition of architecture and software, which is the stuff that's hard to change later. And I like this definition because it's vague yet precise. Because you can look at any element of your architecture and ask it, are you going to be hard to change later? That's an architectural element. So your database is an architectural element. Your web framework is an architectural element, because that's going to be hard to change later. But the way you use that web framework is design. The way you use their workflow class, the way they use their validation stuff, that's all part of design, and that stuff is relatively easy to change later. And this kind of abstract picture captures this concept because the architectural element's here on the bottom, and it's hard to shuffle those gray boxes around without making the entire thing unstable, whereas the red boxes on top, you can move them around and get a slightly different shape, but not change the overall structure. I've written an article series about this topic for IBM DeveloperWorks, which is still available out there. There are 19 installments in this series, and the series is called Evolutionary Architecture and Emergent Design. And that's a really important distinction, because you can't have emergent architecture. You have to have something for everything else to rest on before you can do anything else. But you can create an architecture that you can evolve over time. Design can be much more emergent because not as much rests on design, and so you can actually do less design and let more of it kind of reveal itself to you from code. And I'll show you some examples of that in just a second. But notice that given this definition of architecture, architecture really represents constraints of the things that we can do and we can't do. And so as a corollary to this definition, Martin also said that the architectural elements are the things that are hard to change later, but there should be as little of that stuff as possible, because it represents constraints, and having architectural elements means it's hard to change those things out later. And you know what? Sometimes it's nice to be able to change out big chunks of the system later for something else. And I'm going to talk about some techniques for that, including how those techniques kind of dovetail into a whole continuous delivery topic. That's about architecture and components. First, though, I want to delve into design and spend a little bit of time talking about design in the Agile world And specifically, I want to talk about emergent design. So I should probably give you some definitions here. Webster says that something that is emergent rises or emerges out of something that conceals it. It comes to light. And there's another definition from Webster that says something that suddenly appears, it rises unexpectedly. There are two definitions here, and they very loosely correspond to the two different aspects of emergent design that I'm going to talk about in this talk. One of them has to do more with existing brownfield projects that have been around for a while, emergent design techniques there. The other has more to do with greenfield, brand new projects. So let's talk about the existing brownfield projects first. One of the aspects of design that you probably discovered is that in your application, there's a problem that conceptually looks like this. And you think about this while you're at work, and you think about it while you're driving home, and you think about it while you're mowing the yard, and when your spouse is talking to you and you're supposed to be paying attention to them, there's still some background threads running against this thing, trying to figure out what exactly this thing really is the representation of. And you think about it and you think about it until it finally resolves itself into some sort of structure that makes sense. This whole process of looking at code and deriving things out of it is really this exercise of finding abstractions and patterns that already live and exist there inside your code. Well, let's talk about that for a second. Now, when I'm talking about patterns here, I'm not talking about Gang of Four design patterns. Notice the subtitle of that book, Elements of Reusable Object-Oriented Software. What the Gang of Four guys did was say, looked across a vast swath of software projects and said, you know what, these problems show up in virtually every project, so we're going to create a giant catalog of them because this will be really useful for people building any kind of software. Those are patterns with a capital P. Those are not the patterns I'm talking about here. I'm talking about patterns with a lowercase p. And what I'm calling idiomatic patterns. It's my contention that every piece of software has idiomatic patterns in it, which are just useful abstractions that you found or useful little ways that you found to solve a problem. When that problem recurs again, you'd like to be able to use that same solution again. So it really represents kind of a best of breed kind of, I've created an elegant solution to a problem and I want to be able to leverage and reuse that at some point in the future. I further subdivide these idiomatic patterns into two broad categories, technical and domain idiomatic patterns, where technical patterns are things like validation, security, or transactional data access. Security is a good example of one of these idiomatic patterns because you probably have a very specific way that you do authentication and authorization within your company. You probably do exactly the same way across an entire suite of applications, or you'd like it to be the exact same way across an entire suite of applications. You're working toward that. Most other companies don't really care exactly what the details of how you do that are, but that's a really important thing to your company because that's how you're expected to handle things within your applications. Domain idiomatic patterns are things like business rules and shared functionality across divisions and companies that you discover serendipitously through code. So when used in this way, when I'm using the term patterns, what I'm really doing is describing really effective abstractions. Good solutions to problems that you've encountered before, they're elegant, you'd really like to reuse those guys. And so this is the first aspect of emergent design that I'm going to talk about, is finding and harvesting idiomatic patterns that already live in your code. You just haven't found them yet. And I'm going to show you some techniques for going and finding those things and harvesting them. And this is primarily for brownfield existing code bases. The other aspect I want to talk about is ones for brand new code bases, which borrows from the lean manufacturing and lean software movement, this concept of the last responsible moment to make decisions about things. Not the last moment, but the last responsible moment. The idea here is that the longer you can defer a decision about something, the better potential you have for a better decision because you have more knowledge and context that you've built up over time. Over time, when you attack a problem, you build more knowledge and context. And the longer you can put off that decision, the better potential exists for a decision because you're operating in a place with more knowledge and context. This is one of the really nasty, horrible, hard things in software projects, is you're being asked to produce the most nuanced piece of information at exactly the time when you know the least about the project. You need to come up with architecture and design and estimates before you started working on it. That is exactly the time when you know the least you're ever going to know about that software project is then. Why try to maximize this relationship of the worst possible time to do it, yet do those decisions there, if you can defer those things? Of course, you don't want to defer them too long because then you put yourself into a hole, so that's really this idea of finding the last responsible moment to act on things. And I can't tell you exactly when that is. A lot of that is experiential for Agile tech leads and architects, but I can give you some clues as to when these things pop up, and I'll give you a case study toward the end of a project that I think pretty much nailed last responsible moment. So one of the things you can look at is when you have a component of your piece of software, and in terms of components now, let's just talk about kind of coarse-grained chunk of functionality, the marketing piece of your application, or the sales, or the inventory piece. And over time, that has a certain complexity profile of the amount of work that it's doing, or the crowdedness of the work that it's doing. And as the requirements of this application changes over time, you'll see inflection points of where it's going to take on a lot new responsibility, or it's going to take on some orthogonal responsibilities that it never had before, but now needs to take on those new behaviors. We kind of look at the complexity over time and look for these little upticks. You can see those in requirements as they come through. As the business people build up requirements and whatever ways they capture those, you can kind of see some of these upticks in complexity, and that's a good time to ask that component, is there some part of you that has reached this last responsible moment that I need to replace? Some infrastructure piece or some piece has been acting as a placeholder for what the real ultimate behavior is going to be. And the case study I showed you really took advantage of this looking at inflection points very, very nicely. Part of the problem of doing design up front are the Rumsfeldian unknown unknowns. In fact, if you look at the classic book, Fred Brooks' Mythical Man Month, one of the things he suggests, if you want a really, really killer piece of software, is to write it and then throw that one away and then write it a second time. And there are several interesting characteristics about the second version. One is that it'll be really good. All the design flaws, the architectural flaws you had in the first one will mostly be stripped away in the second one, because you're acting now against all known knowns. There are no unknowns anymore. The second version, you can estimate down to the day of how long it's going to take to write it, because that's the thing that makes estimation so hard, are all these unknown variables that we have floating around all over the place. So one of the things that we're trying to combat here is making decisions when we don't have enough information to make good decisions, because then you have to speculate and guess. So one of the techniques that we use a lot in the Agile world are doing spikes to try to get really quick knowledge acquisition about things. The idea behind a spike, and this is very common in the Agile nomenclature, is a time-boxed experimental coding exercise. So let's say that you've got a requirement on your application, it needs to do geocoding, and you've never done geocoding before in your life, and you are correctly reluctant to just make a wild-ass guess as to how long it's going to take you to do that, because there's a really well-known anti-pattern. It's on the C3 anti-patterns wiki called the Give Me Estimates Now anti-pattern, that says that no matter how many waffle words you put in front of an estimate, like I don't really know, this is a crazy guess, this is just completely out of the blue, no matter how many qualifiers you put on it, as soon as you say a number, you've entered into an ironclad contract that you'll risk your life to make that date come true. And so you want to make sure that you don't commit to that too early. That's the idea of a spike. We've got geocoding. I don't know anything about geocoding, but I need to learn more information, and so I'll create a time box. Maybe it's a 2-hour time box, maybe it's an 8-hour time box. And during that time box, I do nothing but learn as much as I can about geocoding. These spikes are never meant to be prototypes. These never grow into real code. They are designed to be thrown away, meaning that you don't literally throw them away. They're typically done on a branch and version control, but you never merge them back into the trunk, because if you're building it as a prototype, you're going to do non-information gathering activities, like writing unit tests, like writing variable names, more than one character, like writing pretty code that doesn't suck in places. That's not what a spike is about. Spike is about pure, raw knowledge acquisition as quickly as you can. And so we do this a lot to chase away these uncertainties, particularly when you come into things like you need to estimate a part of the system that you're not super familiar with. Spikes are great ways to combat the unknownness of that. The other thing you have to watch out for is technical debt. And this manifests itself on software projects in a lot of very interesting ways. This is a Ward Cunningham metaphor. This idea of technical debt is, imagine what your code base would look like if you could lavish all of your love and attention on it. No refactoring is too big or too small. You want to craft the most perfect code base in the world. The delta between that and what you left to come here is probably a lot of technical debt, which are externally imposed ways that you make compromises on design and architecture of projects. There are a couple of really common drivers of technical debt. One of them is schedule pressure. We don't have time to get it done, so you need to do it as quickly as possible. The other big driver for technical debt is another one of the anti-patterns from the C3 anti-pattern wiki called the boat anchor anti-pattern. The boat anchor anti-pattern says that we've bought this really expensive piece of infrastructure and you have to use this on every project, whether it makes sense to use it on this project or not, because we spent a lot of money for this thing. And a lot of times that ends up driving technical debt because now you're stuck with a bunch of stuff that you don't actually need or don't actually want. Now, in fact, I've started characterizing technical debt in this way, particularly with this kind of common strategy that's out in the world of, so if you need an infrastructure piece, and the case study that I talk about talks about asynchronous messaging. So you need an asynchronous messaging framework, but it's very early in the project, and so you don't know exactly what capabilities you're going to need, and so there's this attitude out in the software world of, well, let's buy the really fancy, expensive one, and then we'll grow into all those capabilities that it offers eventually. A lot of software vendors sell suites like that. The problem with that approach, though, is it ignores the negative impact adding that thing has with all those bells and whistles that are not turned on yet. I've started characterizing that as technical debt, because technical debt are things that are in your project that are not making things any easier, they're just in your way of getting stuff done. And a bunch of bells and whistles and features on a piece of software that you're not using is technical debt, because it's just in your way of doing the stuff that you actually need to get done. In fact, I start categorizing that stuff as technical debt as soon as you add it to the project, and then start discounting it as technical debt when you start using those various features. And we'll see how this plays out as I talk about my case study a little bit later. So that's all a bunch of stuff about last responsible moment. I'll come back to that toward the end as I talk about some architectural impacts. But now I want to switch over to the other aspect that I have of emergent design, which is finding and harvesting idiomatic patterns that already exist in your code. And I want to talk about a couple of different approaches to this. So first, I want to talk about refactoring toward design. So here's a Java method. What it does is not important at all. This is actually a little method from a toy e-commerce site that takes things out of a shopping cart and puts them in an order using low-level JDBC. The point of this is if I want to really do some harvesting and design of this, I've got to clean it up first, because I can't tell what's there. It's just a big lumpy pile of code as far as I'm concerned. Even an experienced Java developer, you'd have to read through more or less every line of code to figure out what's really going on there. You can't look at it and tell what it does, so how are you going to look at it and tell what design is there? So what I want to do is refactor this code to get it to the point where I can actually read it and understand what it does. And so what I'm going to do is, firstly, I'll observe that a bunch of these lines are really just things that kind of conceptually belong together. Here's a really good clue for you. Look at your Java code and look at places where you've added blank lines in your methods. That's a cry for help to make me my own method, because you've added that blank line there because you're saying these 3 or 4 lines conceptually go together. Why not make that a method? And so that's what I'm going to do is take the lines of code that I don't have any blanks in here because of tight spacing, but take the lines that are kind of conceptually together and do an extract method on a bunch of those and get to here. It's a little bit better. It's a little bit better from an abstraction standpoint because now I'm kind of at an even level of abstraction. But there's a side effect of doing this in modern tools, because your refactoring tool has a really strict contract with you. It says, I guarantee that your code will still work exactly the same way it did before when I'm done. And a refactoring tool, when faced with this, a bunch of local variables, the only thing that it can really do is convert those into parameters. And so when you do a lot of refactoring like this, you see an explosion of parameters being passed. That's because, I mean, certainly one of the ways to do this is to move those things to class level, but that has threading and visibility implications that a refactoring tool is never going to take into consideration. But as a human developer, you can. So I'm going to do another refactoring run on this, take some of this shared state and move it out to the class level where it's safe to do in this particular application, and end up here. Now I'm getting somewhere because now I can tell what's actually going on in this code. It does it sets up some infrastructure, does a little bit of work, it completes it, it rolls it back if something goes wrong, and finally it cleans stuff up. This is exactly the code that I had before, only now I can understand what it does. The inspiration for this style of refactoring actually comes from what may be a surprising place for some of you. This is basically Kent Beck's idea of composed method from Smalltalk Best Practice Patterns, which is a book that he wrote in the late 80s or early 90s about Smalltalk. The idea behind composed method is that every public method reads like an outline, and the individual steps are private method or methods that implement those behaviors. And this is really nice and navigable in the Java world now because every major Java IDE, if you hold down the control key, a method name becomes a hyperlink to that method. And so you can literally use this to browse your code, look at it at a really high level of abstraction. If you want to get to the individual details, you just control-click on that method and drill into the details and find out what that method's actually doing. But now that I've got it here, I can see what's going on, and notice that I can very trivially now replace these two lines of code with something else, and what I've built is this little transactional data access method. You couldn't see that before because it was hidden in all that lumpy pile of code, but once you get your code organized, you can actually see it. And so let's talk about harvesting one of these patterns. I'll come back to that one in a bit and convert it to an API, but let's talk about harvesting a deeper pattern. Before I go here, though, I need a little bit of background. I need a couple of metrics. The first one I'll talk about is cyclomatic complexity. This is a metric that's been around for a really long time. It's been around since the 70s in the C world. The idea behind cyclomatic complexity is it assigns a numeric value to the complexity of a function or method. Here's the formula. Thomas McCabe is the one who created this metric. It is edges minus nodes plus 2, where nodes are lines of code and edges are possible paths through the code. So if you have this little Java method like this, if I draw out this kind of nodes and edges view of the world and then count them up, 4 minus 4 plus 2, so the cyclomatic complexity of that method is 2. It's kind of boring when the numbers cancel each other out like that, though. And so let's look at a slightly more complex method in the Java world. I'll draw it out in this kind of edges and nodes view of the world and number them. 8 minus 7 plus 2, so the cyclomatic complexity of this method is 3. It's one more complex than the one that we saw before. So what I have now in my toolkit is a way of determining how complex a particular method is, so I can compare two methods against one another, see which one's more complex. All he's really doing there is measuring loops and other kinds of decisions and adding those as complexity. So that's one metric. The other metric I need is one called afferent coupling. Afferent coupling, if you are a class, your afferent coupling number is how many other classes refer to you. And so in this particular case, the afferent coupling for this class in the middle is 6, because 6 other classes refer to this guy. In some ways, you can look at afferent coupling as a measure of importance. Because if a lot of classes link to you, you're probably pretty important. And with cyclomatic complexity, we have a tool that allows us to determine really complex things. So we put those together, this allows us to go hunting for complex, important things, which is exactly the category of things I want to be able to poke around and find in my software, the really important things that are probably overly complex. So that's what I wanted to do. And I wanted to do this in a way that you could recreate this if you wanted. So there were some very specific characteristics I want to put on this little experiment that I was going to conduct. It needed to be an open source piece of software so that you could reconstruct this if you wanted to. It needed to have been around for a long time, because what I'm really trying to get at here is that my contention is that every piece of software has unharvested idiomatic patterns in it, even if it's been around a really long time. So I wanted a piece of software that's been around for a really long time, that's been used by a lot of developers to build a lot of stuff. And so I chose Struts. It's in its second major release. It's been around more than a decade. Thousands of web applications have been written in this thing. It's in its second major release. You would think that by now most of the major design elements have been chased out of this guy. Let's see. So I downloaded the Struts source code, and I ran a tool on it that gives me my two metrics that I'm interested in. The tool, if you're interested, is called CKJM. It's called that because it's running the Chittimer and Kimmerer object-oriented metric suite. That's the CK, and then JM means for Java. So CKJM is a little freeware tool that you can download and run against any Java code base. The way that CKJM reports cyclomatic complexity, because it reports everything at the class level, is that it gives you the sum of the cyclomatic complexity of all the methods in the class. There are the results for Struts. And if I'm just hunting complexity, the champion here is double list UI bean, which has a WMC as weighted method complexity. That's what CKJM calls cyclomatic complexity. That 66 means if you add up all the methods in this class, the cyclomatic complexity equals 66. So that's what that is. That's the sum of cyclomatic complexity of all the methods in the class. So if I was just looking for complex stuff, here I found it. This is the most complex class there. But that's not all I'm looking for. I'm looking for important stuff too. And if you look across the row, its afferent coupling number is only 3, meaning that only 3 other classes rely on this class to get something done. What if I sort these instead by afferent coupling? Clearly, component is the most important thing in the Struts universe, as being a component-based web framework. That's not surprising. But what I'm really looking for here are high combinations of numbers. I'm looking for important complex stuff. And UI bean immediately catches my eye because it's pretty high in both those categories. So I start poking around in UI bean. I keep meaning to add the Final Jeopardy music to this part of my presentation. I keep forgetting, so if you would just hum the Final Jeopardy music to yourself as we look at the lovely evaluate params method in UI bean and Struts. My favorite part of this method by far is the last line of the method, which is evaluate extra params. It's almost like the developer just got tired of typing. It's like, oh God, I can't type anymore. Okay, evaluate extra params. Okay, I'm done. So if you start poking around in Struts, you'll find a whole bunch of evaluate params and evaluate extra params methods. And what those are there for, Struts is a web-based, component-based web framework, and one of the things it does is auto-harvest some URI parameters for you to fill in form fields and other things. So you can intervene in that process if you want, or you could ignore some parameters that get sent in. That's the combined job of evaluate params and evaluate extra params. As I was poking around in the Struts code base, I kept bumping into one or the other of these two methods in a bunch of different places. So I got really curious. How much of this evaluate param stuff exists in Struts? So I did a little bit of command line judo. Starting in the root of Struts, show me all the Java source files, and within each one of those, show me every one of these that has an evaluate params or evaluate extra params. And there they are. I have found an idiomatic pattern in Struts in the way they handle URI parameters. And I think this is a great example of one of these little idiomatic patterns because a decade ago when they started working on Struts, I'm sure nobody said, you know what, in 15 years, the most complex part of this code base is going to be how we handle URI parameters. Because it seems like such a simple thing. It's so simple, they've solved it over and over and over and over and over again within the Struts code base. So there's a little bit of an epilogue to this story. As I mentioned before, I'm writing this article series for IBM Developer Works, and I posted this about this discovery I'd made in Struts, and one of the Struts committers contacted me and said that he had independently discovered the same thing, that there was a whole lot of complexity around this, lurking around the Struts code base, and so he undertook the refactoring that should have fixed it by now, basically extracting all of this evaluate parameter stuff as an embedded framework inside Struts. And by doing that, removed hundreds, thousands of lines of code and hundreds of cyclomatic complexity points because that was the most complex thing still in Struts, was that parameter handling stuff. And by isolating that in one place, he was able to vastly simplify it. So now that we've seen how to find them, we need to talk about how to harvest them. And you can harvest patterns, these idiomatic patterns, in several different ways. One of which is to just harvest them as an API. which is a nice, easy, convenient way to do it. That's the way you harvest most reusable code. Find a packaging mechanism and a discovery mechanism with your organization where you can reuse that code. You can also do things like annotations, which for some situations make really good kinds of ways to harvest these patterns because they stick out from the code around them, particularly things like validations and other kinds of locality-based characteristics. You'd really like the validation characteristics to live really close to the domain classes, not be separated over here in a web framework somewhere. By creating that as an annotation in the class itself, you have a good locality for that behavior and what it really applies to. And so there are several different ways that once you found these things, you can go harvest them. Which is all about design, but let's go back for a second and talk about architecture. Architecture is this big, huge, vague term in the software world right now. Because when you talk about architecture, you may actually be talking about several different kinds of architecture. One of the kinds of architecture you may be talking about is application architecture, which is how applications get put together. But another kind of architecture you may be thinking about is enterprise architecture. And enterprise architecture, if application architecture is like the architect of a single building, enterprise architecture like city planners. Because as an application architect, you can't come along in your organization and say, hey, I need 80% of the bandwidth of the entire organization because I'm doing this cool thing as my application. Your enterprise architects are going to say, no, you don't get 80% of the bandwidth of the entire organization. Just like city planners won't let somebody build a building in the middle of San Francisco that has a fountain on the top of a 50-story building and sucks up half of the water in the city. They're not going to allow that to happen. So a lot of times this is a policing function as much as anything else. And if you start looking at things like enterprise architecture, one of my colleagues actually put together this mind map of all the things that enterprise architects have to think about in big enterprises, which is a huge, big thing. I'm not going to talk about any of this stuff, particularly all the political stuff that goes into this. What I really want to talk about is how we can actually merge this idea of enterprise architecture and application architecture in a way that solves some problems that we've had in the integration world in the past. And I'm going to do that on the back of some examples from this book. Brian was talking earlier this morning about REST and RESTful kinds of architecture, and that's actually what exactly what I'm going to use here to solve this integration problem at the enterprise architecture level. Before I get into this, though, I need to talk for just a second about Leonard Richardson's RESTful levels of maturity. About 2 years ago, maybe 3 years ago now, at QCon London, Leonard Richardson came up with a scale at how to basically score different architectural styles as to how mature they were against the RESTful scale. So his scale here is REST, so he's definitely biased toward REST. But he scores a bunch of these different architectural styles, and I'll highlight some of these architectural styles very briefly to point out how they've been deficient in solving some really important problems that we've had. So here are his RESTful levels of maturity, where level 0, there's actually 4 levels. Level 0 is a single URI and a single HTTP verb. This is how web services and WS star-based endpoints work. You have a single URI for an endpoint, and you do HTTP post to transfer SOAP documents back and forth, ignoring the rest of the HTTP verbs and all the rest of the HTTP metadata that's there. You're basically just using HTTP as a synchronous firewall-friendly transport protocol for doing remote procedure calls. Level 1 service, you have many URIs but a single HTTP verb. Typically what happens here is that a lot of tools support this kind of behavior where you can point it to a method and say, hey, make this an endpoint for me. And it basically just takes that method name, creates an endpoint for it, converts the parameters into name value pairs that get sent in. This uses a lot of URIs, 1 URI per method name, but typically only uses a single HTTP verb get on top of that. Here, where you get to level 2, you have numerous URIs and addressable resources, and a lot of people get to here and stop and say, we're RESTful, and you are, in fact, RESTful when you get to there. I'll show you some examples of that. And then the last level, of course, is level 3 HADIOS, which is hypermedia as the engine of application state, and I'll talk about what advantage that gives you over just the idea of resource-based computing. Because there's been an evolution of the thinking of this over time. And in fact, the Rest in Practice book talks about this evolution. of these 4 levels on Richardson scale, architecturally, all these guys pretty much fall in the level 0 category. URI tunneling goes in number 1, CRUD web services in 2, and then Hadios in number 3. So let me show you brief examples of each one of these architectural styles. First one I'll talk about is the level 0 guys there, which are different flavors of remote procedure call, or RPC. This is actually one of the things that was a topic of discussion as we were talking about cloud stuff yesterday, is that the idea of distributed objects is kind of a silly idea. We don't have distributed objects. We have distributed data. We don't have distributed objects. You can't send methods. You can't serialize a method, send it along a wire, and execute it somewhere. So a lot of the objectness of our objects gets stripped away, and they become just data containers as we move them from place to place. And so one of the easy ways to model this is just use remote procedure calls. And this is how all of SOAP works, and XML RPC, and a bunch of other protocols. Basically, the idea the client application makes a local method call, which gets translated into an XML document. That gets posted over HTTP, which gets picked up, deserialized, some work happens, serialized back with a payload and a 200 OK, and then deserialized back, and then the local method return there does some useful work. Notice that in this case, all the application semantics reside inside this payload. It is not uncommon to send back an entire XML document just to say, OK, which is kind of a waste of bytes when you think about it, building all this structure just to say that everything went OK. But it basically ignores all of the metadata that's already there in this pipe along HTTP, because one of the things that SOAP was designed for is transport independence, so they actually built up their entire metadata stack around it, because they're not necessarily relying on the underlying transport mechanism to do that. Really, the only difference between XML RPC and SOAP and traditional remote method calls is really just the wire protocol. The wire protocol looks different in all these cases, but the underlying architecture is pretty much the same, where you have XML documents that have things in them, and they get passed back and forth, and of course there are schemas that define what these guys look like. But on the Richardson scale, this scores a 0. This is a very lightweight way to do integration, because it's basically just making remote procedure calls. That's exactly what the mechanism was designed for. It's almost universally interoperable, because all the tools now support this easy way to say, click, make this a web service call, RPC endpoint. Not particularly robust, though, particularly brittle in the face of changes over time, which makes this not a good choice for doing enterprise integration. It also ignores the web as a platform, because most of these protocols were built with transport agnosticism in mind, and so they build up their own metadata stack and their own status codes and all that other stuff. And so this is probably, it's useful for simpler integration problems. When you really do have a remote procedure call shaped problem, you should use this approach. The next one up on Richardson scale is this idea of URI tunneling. A lot of tools make this really easy just by having wizards and other things. Basically, it's using URI as a means of transferring information across a system boundary by encoding it as a URI. So here's the idea. You have a method call somewhere called place order. That basically gets mapped to a method name. The arguments are name value pairs, and those get serialized into some sort of order guy, and then you execute that endpoint. The only real difference between this and RPC is that you tend to have an endpoint per method that you've exposed here, which is not always the case in the RPC world. URI tunneling does use URIs, but only URIs, doesn't use any of the HTTP verbs or any of the other metadata mechanism in that channel. It's not a very sophisticated, in fact, it's very tool-friendly, but not particularly architecturally friendly in terms of longevity and building things that are not brittle. This can be made web-friendly in terms of caching and other sorts of desirable characteristics. But the problem here is really an abstraction, a fundamental kind of abstraction problem, because the URIs are encoding operations here, not resources. And if we're trying to get to the restful world, we're trying to represent those things as resources, not operations. The other thing that this does is violates one of the rules of the web, because typically what happens in URI tunneling is that you do everything over the top of GET, and doing something like place order over the top of GET actually modifies server-side state, which violates idempotence. So you're not supposed to do this. The The gets are not supposed to modify server-side state, and so doing this kind of violates part of the web as a platform concept. So let's march up the next part of the Richardson scale, which are this idea of CRUD web services and starting to treat the world as resources. In the Rest in Practice book, Jim Weber and Ian Robinson have created this mythical place called a Restbucks, which is like a coffee shop, but they're using that as their integration points, integrating between the different roles within the Restbucks world. And here are some of the interactions that they have defined in the Restbucks world, where you can place an order, you can update that order after a certain amount of time, you can pay for it, and you can pick it up, etc. You'll notice that that looks like a state machine. That's actually really common in a lot of RESTful systems, is that you're building state machines and modeling states, because resources move from one state to another state. So that's a very comfortable abstraction on top of resources. Let's say that you are going to piece together what the integration APIs look like for Restbucks. Here, notice we don't just have an endpoint, we also have a verb, because we're taking advantage now of URIs and verbs in HTTP. And so you typically post against order, which creates a new order, and upon success, it sets the location header information in the new order's URI. Notice that what you get back from here when you call this is a 201 created status code that has the location header set that points to the new resource you've created, but no body. There's no reason to send back a body that says everything went okay or has the location of this new order in it, because there's already a header in the metadata envelope in HTTP that handles that for us. And so REST tries to take advantage of all those facilities that are already there. Get lets you specify a specific order and gets that value back. Put lets you update an order at a given URI with new information. And of course, delete lets you logically remove one of those URIs. The idea here, and this is what I was going back to before, is that when you actually do a post in this world to create a new order, it does a create, it sends back a 201 created and sets its location header, but no body comes back, because there's no reason to send a body back. We sent the status back that said, okay, I created a new one for you, and here it is, but there's no reason to send back a particular payload body. You can also, of course, get error conditions here, so we might get a bad request or something like that. There's an entire series, of course, of HTTP status codes you can use for that. So this is basically now the idea of starting to model things as resources in our world, and this really is what he calls CRUD web services. This embraces both HTTP and URIs, so it's using the features of the platform that it's running on, taking advantage and leveraging those. It creates a really good solution to a lot of problems. In fact, anytime you've got simple kind of CRUD operations against resources, this is a perfect model, because you're modeling the resources and you've got the verbs necessary to do operations on the resources. So it's best for these kind of CRUD applications. And in fact, a lot of people in the RESTful world get to here and stop, and that's perfectly fine. You can absolutely say that you have a RESTful system if you stop here, because now what you're doing is modeling things as resources and letting those resources evolve over time as the real entity evolves over time. But there's still one thing that we haven't really attacked, that the last thing it helps us attack, which is this shared, tightly coupled understanding of resource life cycles. And this is a common problem when you're talking about integration. When we're talking about enterprise integration here, here's a fundamental problem in doing that. Think about, for a second, enterprise integration almost as a model view controller view of the world. So you're talking about enterprise integration, so the view part can be kind of thrown away. That's going to be a portal or some application that aggregates other stuff. We don't really care about that. So let's talk about the controller and the model. The model are things like data access and business rules and other kinds of core things that should be facts about what your entities are. And the controllers are workflows, the way you piece those models together. So a controller says, I need these pieces of information from this model and this piece from this model, and I'll tie them together and make them do some work. The problem with that, though, is when you're doing enterprise integration, then your models are really applications that contain some sort of data and logic and other stuff. And now you've got a really fine-grained workflow driven from the client. The client's saying, here are the resources, the things that I need, here's what order to do them in, what methods to call on them. And what that ends up doing is coupling the client and the server together forever. You can't really make a change to one of these guys if this guy is relying really heavily on the details of how that workflow is put together. Because for every one of these workflows, even if the application itself has a workflow in it, there are going to be multiple branch points in that workflow as the user chooses different options or different things. There's no, the client can't really, in our current world, that's not exposed to them. So basically we're saying that applications can own their business logic, but not their workflow. We're trying to extract the workflow up to the client because he has to be able to drive the decision-making process with interactivity with a user or another system. What a lot of vendors have tried to do is look at this problem and say, oh, you know what, that's a big problem, we got a solution for you. And the solution is worse than the problem. Things like BPL and BPM, and basically any kind of cartoons to code kind of scenario where you're supposed to draw a picture and then it's supposed to vomit out a bunch of code that does work. These are really dangerous because they demo really great, and then you try to use them for a real problem and you end up with a giant hairball effect, which is there's so many lines intersecting that you can't get anything useful done with it. And now you've actually put yourself in a much worse situation, because now once you've got your workflow captured in this graphical tool, it is no longer testable. You can't write a unit test for that stupid diagram that you've got. You can't really diff it either. Now, underlying that stupid diagram is a 10,000 line XML document. You can diff the 10,000 line XML document if you want, but that's a job with a high suicide rate. Nobody wants to do that. There's no good way to see that diff graphically, so now you're in this XML kind of world. You can't easily refactor this stuff. And so what happens if you have one of these diagrams somewhere and there's another piece of behavior that's almost the same but a little bit different over here? There is no extract method and use commonality, so you're left with copy and paste coding. You copy this workflow and then paste it over here and make a small change to it, but now you get this proliferation of different, almost one-off versions of these work processes. So I don't think this is even usable, and it still doesn't attack this fundamental problem that applications own their business logic but not their workflow. That's where this Hadios idea comes in. And I've said that anytime you create an acronym with the word hate in it is probably not a great thing, but this is just kind of a side effect. It really is an acronym that means hypermedia is the engine of application state. Here's the idea with Hadios, is that rather than doing integration at the method level against our models, against our server applications, let's do it at the process level instead. The idea of Hadios is that when you send things back from the server, you send back still data because you care about data, but the other thing you send back are links. And those links lead you to subsequent workflows within this application. So let's say this application does something about ordering. When you place an order at RestBucks, you've got two options. You can either pay by credit card or pay by cash. Those are two different branching workflows that live in this application that models things about payments. What Hadios is going to do is say, once you've placed an order, there are two things you can do in my universe. You can pay by cash or pay by credit card. I'm going to send you back two links. If you follow one link, you pay by credit card. If you follow the other link, you pay by cash. That's going to take you to a resource that handles the details of what that interaction is. That's the idea behind hypermedia, is that when you make a request to one of these resources, what you get back is data, but also a bunch of links about subsequent steps within the workflow. Now all your client becomes is the entry point to a workflow that is defined and lives forever on that server application that knows the real details of that workflow, the validations, the data access, all those other things. What it's doing, what Hadios lets you do, is expose that workflow to the rest of the world in a link-based way, so that now the client can say, okay, I've placed the order, now the option comes back to pay, I'll take the payment option. Now that comes back to, well, there's no payment anymore, but the state machine says, okay, now I can pick it up, and so you're just moving from state to state over time, and the next state that's possible comes back to you in links every time you make a call to one of these resources. What you're really doing here is establishing contracts between things. And so we're used to contracts looking a different way in other kinds of integration world, but contracts are really just a combination of protocols. A protocol in this world consists of HTTP idioms like verbs and metadata, entry point URIs that get you to the beginning points of workflow processes, and then the subsequent steps come back to you as links within that as a hyperlink. And then media types, which define what the shape of the data looks like. This is what we use DTDs and XML schemas for in the kind of traditional integration world. That's media types are used in the hypermedia world. And those media types really specify things like schemas, processing models, and how link relationships work. But it's really just the same schema stuff that we're used to before, cast in a different light. And in fact, you don't even have to use media types here. You can use traditional kinds of XML schema if you want, which we end up doing in a lot of cases. Excuse me. But the point of this is the core of any contract are what formats do you accept, what's the processing model, and what kind of controls can I use. So if you take this and apply it to the exact example from the Rest in Practice book, RESTBucks, what you see, what ends up happening is, excuse me, excuse me, these URI map onto business processes. These business processes are basically just a state machine. Because anytime you're dealing with resources, you're really talking about moving a resource from one state to another state, which is a great model for a state machine. That's really all we're building when we build one of these systems, is building a state machine and defining what possible states you can go to next. This is actually really nice architecturally because building state machines helps you think about all the states that you should accommodate for that resource, because resources have a certain number of valid states. Now you can start thinking about, what is the delete state for this particular resource. And so the links that come back define the kind of interactions you can have with the application. So for example, if I place an order, what I'll get back is a way to make a payment or a way against this URI to either get the current status on it, do an update for it, or delete that order. So this is what a snippet of that hypermedia document looks like that comes back. It has coffee information in it, but it also has these domain application protocol links, what it's related to, what the URI is, and what media type it's expecting. This tells you the details about what the thing's going to look like, what shape it is from an XML standpoint, its schema, its DTD, or whatever that is, which lets you do validation as you make calls to these resources. One of the nice things about this as an enterprise integration architecture is because it relies heavily on state machines, it's usually, if you have a well-constructed application, just kind of lay this integration logic as a facade over your existing system. You basically take those resource concepts that you want to support, implement those internally for your code, and then build a state machine facade over the top of them and call into those to get it to do work. So what this gives you is evolvable application integration. What this allows you to do is say that I've decoupled now the life cycle from my client and my server. Because let's say that you're in the RESTBucks universe and we're using an internal credit card payment processing service. And when you place an order in RESTBucks, what you get back is a link along with a media type that says, okay, if you want to make a payment, you follow this link with these data types and you can make a payment. We change at some point to use an external credit card processing facility. We change the server to now send a new link and a new hypermedia type back to the client. But all the client knows is that when you want to make payment, you follow this link. That it got changed is irrelevant to the client because the client knows I send this link with this information and I get payment information back. And so that allows you to decouple the evolution of the server application and the client application so that they can evolve independently, and you can support multiple versions against the server and some other nice tricks like that. So remember when I was talking about this diagram earlier, I said that the architectural elements were the things that are hard to change later, and you want as little of that stuff as possible. Because architectural elements represent constraints. So one of the ways that you can do this is try to isolate orthogonal concerns and basically componentize them. Let me show you what I mean by that with this case study. This is a case study for a project that I've worked on variously for the last 4 or 5 years. This is a project that's running in our office in Atlanta right now for a company called OVE.com, onlinevehicleexchange.com. This is the wholesale version of autotrader.com. If you own a car dealership and you want to auction cars to other car dealerships, you can get a login on this site. So they do car auctions is what they do here. And there's a really fascinating story about how the asynchronous messaging evolved in this application. So the very early days of this application, the users wanted a sense of progress. This is an auto auction application, and for car dealerships, it's not atypical for them to upload 100 cars at a time with 50 photos each, and nobody wants to look at an Ajax spinner for an hour and a half, so they wanted some sense of progress or the ability to start a job and then come back later and see if it's done. That's classical kind of asynchronous messaging, and so the tech lead met with the developers on the team. It was suggested that we should add a message queue, but they did a couple of spikes. Somebody found this little thing called background RB, which basically sets up a very simple single message queue backed by a relational database. And they said, you know what, for the simple problem we have, that's good enough. But this wasn't the tech lead's first project. He figured pretty definitively that we'll eventually need to replace this simple mechanism with something else, and so he was careful to put it behind the Ruby equivalent of an interface. About a year into the project, a little over a year, a second kind of asynchronous behavior popped up, the ability to do timed events like cron job kinds of things. We built that on top of background RB after spiking to make sure it would still handle that, and it did, so that was fine. But then about the 2-year mark on the project, a third requirement popped up for asynchronous messaging, which are constantly updated things like cache values and counts and things like that. At the same time that came about, the background RB infrastructure was starting to creak a little bit. In fact, we'd been using this simple message backed by a database for a long time. Our DBAs, though, had caught wind that we're using one of their precious databases as a message queue, and they started making this face at us every time we pass them in the hall, which we view as probably not a good thing for the project's longevity. And so that was the impetus for us to switch to a real message queue, Starling, which is a message queue in the Ruby on Rails world. But notice what happened there. A couple of things actually happened that were of interest. Notice at the very beginning of the project, the main characteristic is you don't know what you don't know. So a lot of projects just in a knee-jerk way say, well, let's buy the fanciest piece of infrastructure we can just in case we need all that capability later. But I talked about this before, that when you do that, you basically take on a bunch of technical debt that you don't start paying back until you start using all those advanced features. The problem, though, is you don't know which of those advanced features you're eventually going to use, and so in a lot of cases, organizations end up paying money for technical debt that they never justify. They never end up using that advanced feature, but they always end up working around it every time they touch this tool, which is just the definition of technical debt. There's another observation I'll make here as well. Remember I said that architectural elements were the things that were hard to change later. And messaging infrastructure is definitely an architectural element, something that is traditionally hard to change later. But the tech lead on this project knew that background RB was not going to be the horse they rode into the sunset. He knew that it was a temporary, it's good enough for right now. So when he put that in place, he was careful to put that behind a facade, behind an interface, so that when it came time to switch this out, it took one pair of developers less than a week to swap out background RB with Starling. By putting it behind an interface, he basically converted it from an architectural element into a design element. And that's exactly what you want to do, convert things that are hard to change later into things that are easier to change later. And that's exactly where the continuous delivery guys are trying to go with a lot of things they're talking about building component-based architectures. And so I will talk about this in great depth on my workshop on whatever day I'm doing workshops, a couple of days from now, on continuous delivery. But this is the idea of the continuous delivery world, of this idea of doing automatic builds. This is what we know of as continuous integration now. But as we get further and further along these builds, we're going to do more and more sophisticated kinds of tests and builds for things. What we'd eventually like to do, though, is stop doing hyperactive builds here, stop building the entire application every time, and eventually get around to this idea of continuous integration at the component level. If you can build component-based architectures, what you do is make the architectural pieces relatively easy to swap out for other ones. And you make those architectural pieces easier to build independently of the rest of the application. What we'd eventually like to do is get to this place where your application consists of several coarse-grained components, each of which has its own life cycle. It has its own build kind of semantics, it has its own environmental semantics, and a change in this guy automatically triggers a build and a pipeline for this dependent application, you're actually cutting down on the amount of code that you're doing every time and isolating changes behind those component barriers so that you have less coupling across the components of your application, which is obviously a desirable architectural characteristic. So I'll leave you with this. Actually, let me back up one. Back in 2006, I kind of accidentally repopularized this term polyglot programming, this idea that when we have really super powerful runtimes like Java, then you can start mixing and matching languages on that runtime. And my colleague Ola Benny, when I came out with my polyglot programming post, came out with a pyramid where he suggested that maybe you want more statically verifiable languages on the bottom, easier to use dynamic languages in the middle, and then DSLs kind of riding on top of all those. And I think this is a really, really perceptive observation. But this was 2006, and I actually think this has changed. In fact, my pyramid today, I actually think the static versus dynamic thing is kind of a red herring. My pyramid today would say that you have functional code on the bottom, because this is programmatically verifiable much more rigorously than any kind of static typing is. So this is a Clojure or Scala or something like that. Imperative languages like Groovy or Ruby on the top to do things like user interfaces and the things that you don't need as much hardcore verifiable accuracy, but you need productivity. And then DSLs riding on top of that still, but actually I think the DSLs don't just ride on top, they actually pervade the entire stack now. So you see a lot of DSL techniques in functional programming languages. Things like data access, SQL libraries that are done very functionally. And so I think you're going to see DSLs kind of leaking through all this stuff. And the nice thing about functional code is that it tends to encourage this idea of creating component-based architectures with good, clean boundaries between them. And so ultimately, I think my goal, this is kind of my entire landscape of the world, is that application architecture is going toward functional on the bottom, imperative in the middle, with DSLs kind of pervading all those layers, using these emergent design techniques. Enterprise application uses the web as a platform, using component-based development, and this entire thing is wrapped in a big continuous integration feedback loop. That's the kind of idea that we've got on what Agile architecture and design looks like now. Thanks very much for coming. I hope you enjoyed it. Okay, thanks.